hard and soft acid and bases. The term acid and bases are routinely used in our daily life. Chemists have been classifying substances as acid and bases since long time. Lavoisier noted that the common element in all acid was oxygen. The word oxygen in Greek means acid former. However, Humphrey Davy showed that all acid contain hydrogen. It was in 1884 Arrhenius developed the theory of acid and bases. Note that today properly as Arrhenius theory of acid and bases. According to Arrhenius, an acid is a substance which give hydrogen ion in aqueous solution, and base is a substance which give hydroxyl ion in aqueous solution. The strength of an acid or base depend upon its capacity to provide H positive and OH negative ion respectively. The process of neutralization of an acid by a base can be represented by the equation reaction H positive plus me OH negative ion is equal to H2O. In 1923, J. N. Bronsted and T. M. Lowry independently proposed a new acid-base theory. According to their theory, an acid is a proton donor, whereas base is a proton acceptor. The acid-base reaction is regarded as a proton transfer reaction. In 1923, G. N. Lewis gave another general definition of acid-base behavior in terms of electron pair donation and acceptance. However, this theory got the recognition only in 1938. According to Lewis, an acid is a substance which can accept a pair of electrons, while a base is a substance which can donate a pair of electrons. In other words, an acid is an electron pair acceptor while a base is an electron pair donor. The earlier definition of acid and base were solely based upon the observable properties such as taste, ability to dissolve substances insoluble in water, and their effect on vegetable dyes. The term acid was applied to substances they have a sharp or sour taste. The turn blue, litmus red, react with certain metal to liberate hydrogen gas, and have the ability to dissolve substances insoluble in water. On the other hand, the term base was applied to substances that have a bitter taste. Soapy smell, turn red, litmus blue. However, tasting and feeling chemical are dangerous method of determining whether the substance is an acid or a base. You should never ever taste or touch solution of chemical in laboratory. There are, however, other method of recognizing acid and bases. For example, acid and bases change the color of certain dyes known popularly as indicators. One of the most common indicators is a vegetable dye obtained from lichen known as litmus. Aqueous solution of acid turn the litmus red, whereas aqueous solution of bases turn it blue. Thus, any substances which has an unshared pair of electron can act as Lewis base, whereas substance which has an empty orbital to accommodate a pair of electron act as Lewis acid. In other words, substances capable of donating a pair of electrons are regarded as Lewis base, and substances capable of accepting a pair of electrons are regarded as Lewis acid. Acid base or neutralization reaction may thus be regarded as donor, Lewis base acceptor, Lewis acid reaction, or coordinate covalent bond formation reaction. The classical example of a Lewis acid base reaction is that of between boron trifluoride and ammonia. Using electron dot diagram, we can see that boron trifluoride is the Lewis acid and ammonia is the Lewis base. NH3 plus में BF3 gives NH3 coordinate bond BF3, donor acceptor or coordinate bond formation reaction. Lewis concept of acid and bases is very commonly used because of its simplicity, and the ease with which our formation of coordination compound can be explained. In brief, all the usual ligands can be regarded as Lewis bases, whereas all the metal ion can be regarded as Lewis acids. The degree of affinity of a metal ion for ligands can be termed as Lewis acidity, and the tendency of the ligand to combine with the metal ion can be regarded as Lewis basicity. Hard and soft acid and bases and acid base reaction according to Lewis concepts involve the reaction between a donor A and a acceptor B is to form a complex as given below. A plus B gives AB. The formation of the stable complex between the donor A and the acceptor B depend upon the nature of species A and B involved. It has been known since long that certain ligands form more stable complexes with metal ions such as Ag positive, Ag2 positive, Pd2 positive and Pt2 positive. On the other hand, certain ligands form stable complexes with metal ions such as Al3 positive, CO3 positive and Pt4 positive. Based upon the preferential bonding, the acid and bases have been classified into two groups, class A and class B, according to their preference. Class A metal ion include alkali metal, alkyne earth metal, lighter and more highly charged ion, for example Ti4 positive, Cr3 positive, Al3 positive, Fe3 positive, CO3 positive, etc. Hydrogen ion H positive. Class B metal include heavier transition metal of second and third transition series, Cd2 positive, Hg2 positive, Fe2 positive, Pt2 positive. Heavier transition metal in lower oxidation state, Ag positive, Hg2 positive, Cu positive. Low valent metal ions such as zero valent metal ion in metal carbonyls. Depending upon the type of metal ion, ligand can also be classified as class A and class B depending upon their preference. Class A ligand include molecule or ion with donor atom NOFCl, etc. It is important to note that class A ligand prefer to form strong complexes with class A metal. Class B ligand include molecule या ions with donor atom P, AS, S, Se, I, etc. Class B ligand prefer to form complexes with class B metal ions. It was in 1963 Pearson coined the term hard and soft acid and bases for class A and class B metal ion and ligands respectively. Accordingly, class A metal ion are referred to hard acid while class B metal ion are called soft acids. Similarly, class A ligand are named as hard bases whereas class B ligand are termed as soft bases. In summary, according to Pearson, class A acid are hard acid H positive, La positive, Na positive, Be2 positive, Mg2 positive, Cr3 positive, Fe3 positive, etc. Class B acid are soft acid, Ag positive, Pd2 positive, Co positive, Pt2 positive, etc. Class A bases are hard bases, H2O, NH3, F negative, ROH, etc. Class B bases are soft bases, R3P, R3AS, R3S, R2SE, I negative, SCN, etc. Classification of acid and bases as hard and soft. Pearson observed that it is possible to correlate acid base interaction on the basis of hard and soft acid and bases. He observed that type A metal ion, that is acid, were small, compact and very polarizable, and these preferred ligand that were also small and less polarizable. He called these acid and bases as hard. On the other hand, the type B metal ion and the ligand they prefer appear to be a larger in size and more polarizable. He described these acid and bases as soft. Pearson generalized the acid-base relationship and expressed that as hard acid prefer hard bases and soft acid prefer soft bases. Classification of acid: a general classification of some common hard and soft acid along with some border line cases in the table 4.1. And its inspection of table 4.1 revealed that hard acid usually have the following characteristics. Ha- Hard acids are cations of smaller size or lighter elements. Hard acids are cation of higher oxidation states, for example, Cl3 positive, Cl7 positive, IF positive, I5 positive, and I7 positive. Hard acids are molecule या cation with lesser number of valence electron. Hard acid hold the valence electrons tightly and consequently are not easily polarizable. In summary, hard acids bind strongly to a proton. Hard acids are small sized, compact, and are not easily polarized. A close look at table 4.1 also revealed that soft acid possesses the following characteristics. Soft acids are cation of the large size or heavier metal. Soft acids are cation of lower charge. Soft acids are molecule या ion with large number of valence electrons. Soft acids do not hold the valence electron tightly and are therefore easily polarizable. In summary, soft acids are large sized and easily polarizable ion या molecule that bind strongly to highly polarizable ion या molecule. It is important to note that there is no sharp division between hard and soft acids. There are a number of Lewis acids that are neither too hard nor too soft acids. Such type of acids that are neither hard nor soft are called borderline acid, which are shown on the extreme right of table 4.1. Borderline acid have property which are intermediate between that of a hard acid and a hard base. In case of borderline acids, the properties such size, oxidation states, and polarizability of the cation या molecule are neither too low nor too high. On the other hand, soft acid will show the opposite and trend, and the following order of preference for binding the donor atom या ion within a group is observed. I negative much greater than Br negative greater than Cl negative greater than F negative. R2T much greater than R2SC greater than R2S greater than R2O. R3SB greater than R3AS greater than R3P greater than R3N. The above trend can be pictorially represented as question 4.1. With what type of interaction do you expect between a hard acid and a hard base? Since both hard acid and hard bases are not easily polarizable, their interactions are predominantly ionic. Question 2. What type of interaction do you expect between a soft acid and a soft base? Answer. Since both soft acid and soft base are usually polarizable, the interaction between them are predominantly covalent. Classification of bases. A general classification of some commonly used ligands, Lewis base, into hard and soft bases, etc., with the borderline basis is presented in table 4.2. A glance at the table 4.2 reveals some of the important characteristics of hard bases. Hard bases bind strongly to the proton. Hard bases contain donor atom of high electronegativity. The donor atom in hard bases possesses low polarizability. The hard acid bases are not easily oxidized. Hard bases contain empty orbital of high energy. In summary, hard bases bind strongly to a proton. The donor atom in case of hard bases is of high electronegativity and of low polarizability. A further inspection of table 4.2 revealed that the following features are observed in case of soft bases. Soft bases contain donor atom of low electronegativity. Soft bases contain donor atom of high polarizability. Soft bases get easily oxidized. Soft bases are associated with empty low-lying energy orbitals. In brief, soft bases contain less electronegative nonmetal including C, S, P, and I. The donor atom in such bases possesses donor atom that are easily polarized. Just as there are borderline acids, there are borderline bases also. The property of borderline bases are in between those of the soft and hard bases. It is important to note that the category are not divided. For example, the halide ions form a series from the very hard fluoride ion through the hard borderline chloride ion to the borderline bromide ion and the soft iodide ion. The Soft acids, also known as class B metal, and are the group of metal ion that are in the lower portion of the metallic element as shown in figure 4.1. The classification of the HSAB acid ions into a hard white, borderline shaded, and soft black. Pearson HSAB principle. Pearson proposed a simple rule for predicting the stability of coordination compound formed between acids and bases. This rule is quite often named as HSAB principle. According to Pearson HSAB principle, hard acid prefer to bond with hard bases while soft acid prefer to bond with soft bases. It is important to note that hardness and softness of acid and bases refer only to hard and soft interaction. It is by no mean related to the strength acid and bases. For example, both F negative and OH negative ions are hard bases, but the basic strength of OH negative ion is nearly equal to 10 raised to power 13 times that of F negative ion. In other words, hard acids will show the following order of preference of binding the donor atom, the ion within a group: F negative much greater than, Cl negative greater than, Br negative greater than, I negative, R2O much greater than, R2S greater than, R2Se greater than, R2Te, R3N much greater than, R3P greater than, R3As greater than, R3Sb. Application of HSAB principle. Pearson principle of HSAB has a number of application in inorganic chemistry. Some of these are discussed below. First, stability of the complex. We have already noted that hardness and softness of acid and bases are related only to the hard and soft interaction. Hardness and softness of acids and bases has nothing to do with the inherent acidic or basic strength of acid or bases. For example, both OH negative and F negative ions are hard bases, although OH negative ion is for stronger a base than F negative ion. In fact, OH negative ion is 10 raised to power 13 times more stronger a base than F negative ion. However, in HSAB principle, both OH negative and F negative ion are at par with each other. Pearson in 1963 explained the relative stability of coordination complexes on the basis of HSAB principle. Let us consider a general reaction between a Lewis acid and a Lewis base. A plus B gives AB complex. The complex AB will be most stable if A and B are either both hard and or both soft. The complex AB will be least stable if A is hard and B is soft, or A is soft and B is hard. For example, a complex behaves a soft acid Ag positive and soft base I negative ion is quite stable in contrast to the one between soft acid Ag positive and a hard base F negative. Ag positive soft acid plus 2I negative soft base gives AgI2 negative stable complex soft interaction. Ag positive soft acid plus 2F negative hard bases gives AgF2 negative unstable complex soft hard interactions. Similarly, the reaction between LiI and CSF resulting in the formation of LiF and CSI constitute and interesting example suggesting the preferential stability of soft and hard combinations. LiI hard soft plus CSF soft hard gives LiF hard and CSI soft. Some of the other important reactions suggesting the stability of the soft and hard interaction are given below. CUIT hard soft plus CUF soft hard gives CUFT hard plus C2CUI soft. CAS hard soft plus H2O hard gives CaO hard plus H2S soft. BeI2 hard soft plus HgF2 soft hard gives BeF2 hard plus HgI2 soft. The rule of thumb in determining the stability of the complex is the preferential formation of hard and soft interaction. Exercise: why C of F6 to negative 3 negative complex is more stable than COI6 3 negative. Solution: In both the complexes COF63 negative and COI63 negative, the oxidation state of cobalt is plus 3. CO3 positive is a hard acid, therefore, it combination with a hard base, that is F negative, will lead to COF63 negative, which is a hard interaction. On the other hand, combination of CO3 positive with a soft base I negative will lead to COI63 negative, which is a hard soft interaction. The COF63 negative is more stable than COF63 negative. It also has been noted that the combination of hard or soft ligand with a metal ion is always preferred over a combination of mixture of hard and soft ligand with a metal ion. For example, the complexes COCN3 5 3 negative and CONS3 whole 5 F2 negative are far more stable, whereas the complexes COCN whole 5 F3 negative and CONS3 whole 5 I positive are unstable. This is because Cn negative and I negative are both soft bases, whereas NS3 and F negative are both hard bases. Classification. Second, a classification of acid and bases. The acid and bases can be classified as hard or soft depending upon their preference for hard and soft reactions. Let us consider the following reaction. BH positive plus CH3 Hg positive gives CH3 Hb positive plus H positive. We already know that H positive is a hard acid, whereas CH3 Hg positive is a soft acid. If B happens to be a hard base like NS3, the reaction on the left hand side will be preferred, that is NH4 positive plus S3 Hg positive, CH3 Hg positive, NS3 plus H positive. Conceptually, ammonium can be written as NH4 positive gives NH3 hard base plus H hard acid, which means the formation of NH4 positive is preferred because of hard acid H positive and a hard base NH3. On the other hand, if B is a soft base like R2S, the right hand side reaction will be favored as shown. R2SH positive plus CH3Hg positive gives CH3HgSR2 plus H positive. Conceptually, CH3HgSR2 positive can be written as CH3HgSR2 positive soft acid base gives CH3 Ag positive soft acid plus Sr2 soft base, which means the formation of CH3 HgSr2 is preferred because of soft acid CH3 Ag positive and a soft base Sr2. Similarly, an acid A can be classified as hard or soft depending upon the direction of equilibrium. AF plus SCN gives ASCN plus F negative. We know F negative is a hard base and SCN negative is a soft base. If A is a soft acid like Ag positive ion, then the above reaction in the forward direction is favored. AgF soft hard plus SCN soft gives AgSCN soft plus F negative hard. Conceptually, AgSCN is formed through soft interaction. Hence, according to HSAB theory, the reaction is preferred in the forwarded direction. On the other hand, if A happens to be a hard acid like Na positive ion, then the forward reaction is not favored, rather the backward direction is preferred. NaF hard plus SCN soft NaCN hard soft plus F negative hard base. Conceptually, NaF is formed through hard interaction. Thus, according to HSAB theory, the reaction is preferred in the backward direction. OH negative is much stronger base than SO3 2 negative and hence cannot be displaced by weaker base SO3 2 negative. This reaction, however, is favored by HSAB principle. CH3CdOH soft plus SO3 2 negative soft gives CH3CdSO3 negative soft plus OH negative hard. It is important to conclude at this stage that Lewis acid Lewis base reaction are governed by two independent principles. First, strength of the acid or base. Second, softness and hardness of the acid or base. The definition of hardness primarily uses the idea of polarizability, which states that a less polarizable species is hard and a more polarized is soft. For ions of similar charges, the ratio of the charge to radius should be used to assess the relative polarizability or relative hardness or softness. However, HSAB principle does not take into consideration the quantitative idea of relative hardness or softness of the species. In summary, the major limitation of HSAB principle is too general and without any qualitative scale of measurement. HSAB principle does not take into consideration the acidic or basic character of the compound. HSAB principle failed to explain the feasibility of the reaction CH3 positive plus H2 gives CH4 positive plus Hg. Delta H 86 kilocalorie per mole in spite of the soft CH3 positive H negative interaction. It is probably the greater acidity of proton H positive relative to HCH3 cation that is responsible for the unfavorable reactions. Thank you.